Okay, so today on campus, the students here in class did this enrichment set, which can also be found on the course website. We did enrichment on alcohols. So what I suggest if you're watching this video online is to pause it, try it for yourself, and then resume when you're ready. So in the first part, we were determining if the names were correct. There's the next 4. And there's the last one. Then in the next section, we were determining the relationship between pairs of molecules. And there's the next 2. And then the last part, we were writing reactions, determining what type of reaction that was and all the good catalysts that we would need. So you can also download this file from the course website and go about it that way as well. And now we're going to go over these problems and decide if we got them right. So, first one. The way I recommend doing these is to draw it as written and then decide if the name that you give matches the name that you were given. So, pentanol, 1, 2, 3, 4, 5. 4 bromo, 1, 2, 3, 4. 3 ethyl, 4 pentanol. All right, is the name of this the same as the name of that? No, this name is incorrect. What mistake did the student make?
Numbered from the wrong side.
Right. Numbered from the wrong end. We should number here, right? 1, 2, 3, 4, 5. So what should the name be? So we numbered from wrong side. What should the name be?
2 bromo.
2 bromo. 3 ethyl. 2 pentanol, right? They just numbered from the wrong side. All right, let's draw the next one. Hep, it's 7. 1, 2, 3, 4, 5, 6, 7. 2, 2-dimethyl. And 4 ethyl. 1, 2, 3, 4. And 1 heptanol. Okay, if we name this 1, 2, 3, 4, 5, 6, 7, we would number this way. It would be 2, 2-dimethyl, 4 methyl, 1 heptanol. So is this name correct? Yes. Okay, cyclohexanol. Hex would be how many? 6. And hexanol, 5-methyl, 1, 2, 3, 4, 5. Is that name correct?
Number 3.
On number 3, yes. Should it be 5-methyl?
Oh, 4-methyl.
It should be
3.
3-methyl, right. Numbered the wrong direction, right? It's incorrect. What mistake did the student make? They numbered clockwise. Should number counterclockwise, right? So the name shouldn't be 5-methyl, it should be what? 3-methyl, right? They just numbered the wrong direction. All right, let's go through the next few. All right. X is 7, excuse me, 6. 1, 2, 3, 4, 5, 6. 1, 1-dimethyl, 2 hexanol. Well, I see an immediate error. What's that? Right, you can't have a methyl group on carbon 1, right? Incorrect. So you could word this a lot of different ways. You could say miss ID the chain, or you could say can't have methyl group on C1, right? That's saying the same thing. So this isn't a hexanol. What is it? Right. So it should be 1, 2, 3, 4, 5, 6, 7. So the name should be, right, 2-methyl-3-heptanol. And just remember, if you want to split it up, you could name it 2-methyl-heptan-3-ol if you wanted to do it that way too. Okay, pent, that would be 5. 1, 2, 3, 4, 5. 1 bromo. 4. 1, 2, 3, 4. Is that correct?
No.
No, that's incorrect. What's the mistake?
It should be 5 bromo 2 pentanol.
Right, you give priority to the OH, right? So you number from this side. 1, 2, 3, 4, 5. So it should be 5 bromo 2 pentanol, right? Okay, cyclopenta, so that's 5 and it's in a ring. 3, 4, well, that just doesn't make sense, right? 3, 4, where are you picking carbon number 1 from? I mean, that's just arbitrarily ridiculous, right? This is obviously incorrect. What's the mistake here?
There's supposed to be one of those has to be carbon number 1.
Right. Give lowest numbers. So you could go 1, 2 or 1, 2 either way, right? It should be 1, 2 cyclopentadiol. We good on these? All right. Now we're looking at structural. Oh, wait, no, we still got 2 more to go. Octa, so that's 8. 1, 2, 3, 4, 5, 6, 7, 8. 3-methyl, 1, 2, 3. 2, 2, 8. 2, 2, 8. Is that name correct?
I didn't know. Do you number from the other one because that one's first?
Yep, this has to get priority. Right, remember from this direction. Numbered from wrong side.
I didn't know if you do it that way or number from the other side. So
This gets you to your first alcohol first. Yep. So even though there are 2 of them here, this alcohol gets you. This side gets you your first alcohol first. So it should be 6-methyl. What? 177. Right. 6-methyl 177. And then cyclohexa, that'd be 6-membered ring. A diol. 1, 2, 3, 4, 5. Is that correct?
No.
No. What's the mistake here?
1 through the number wrong.
Right. Numbered wrong way. Right. So it should be 1, 2, 3. 1, 3. Cyclohexadiol. Good. Are we good on those 2? All right, now we're going to look at relationships. If they are the same, if they are unrelated, or if they are structural isomers. Those are our choices. What are these 2? They're the same, right? One's just the same molecule rotated, right? They're both what? It's the same one we just did. 1,3 cyclohexadiol. Right, they're both 1,3 cyclohexadiol. All right, let's move up. Let's go through the process here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's C9. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And now let's count here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, so they have the same formula. So what does that mean immediately? Well, if they have the same name, they'd be structural isomers, right? They definitely have the same formula, so there definitely is a relationship. Do these two have the same name, though? Let's name 1, 2, 3, 4, 5, 2, 3, 4, 1, 2, 3, 4, 5. We number this direction, we get 3 substituents. If we number this direction, we only get 2 substituents, so we want to number horizontally. So this would be what?
2, 3, pentanol.
1 pentanol, right? And then this one would be 1, 2, 3, 4, 5, 6. We're going to get 6 that way. So this would be what? 3-ethyl, 4-methyl, 1-hexanol. They have different names, same formula, so what must they be? Structural isomers, right? If they had the same name and the same formula, then they'd be the same molecule, right? But if they have same formula, different names, that's why we conclude that they're structural isomers. All right, let's look at these two. I don't even think we need to go through the process of naming these. I think we can just look at it and tell what are they.
They're not all.
Are you sure?
Oh, structural isomers.
They're structural isomers, yeah. And here's why I can conclude that. Right? They each have an alcohol. They each have a fluorine. They each have a chlorine. They each have a methyl. They're both 7-membered rings. But notice it goes fluorine, alcohol, methyl, whereas it goes fluorine, alcohol, chlorine here, right? So the order is different, but they've got the same formula. So we could go through and name them, but just by looking at it, you can tell that those have to be structural isomers. They have the same stuff. It's just in different orders. So the only difference is going to be the numbering. That's going to be the only thing that will differ. And then in this one, let's go through and count our carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's C10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So they have the same formula. Now we just need to decide, are they the same molecule or are they structural isomers? So let's name them. 1, 2, 3, 4 versus 1, 2, 3, 4, 5, 6. Obviously, we're going to number this way, right? So this would be what? 6-methyl 4-nonanol, right? And then with this one, 1, 2, 3, 4 versus 1, 2, 3, 4, 5, 6, right? So this would be 2-methyl 4-nonanol. So therefore, these two are structural isomers. Good. Questions on that kind of problem? Same formula, different name. All right, last part we're going to do reactions. All right, we are trying to make this molecule. Hep, that's 7, 1, 2, 3, 4, 5, 6, 7, 2, 3 dimethyl, 2, 3 dimethyl, 3 heptanol. Okay, what kind of reaction produces an alcohol?
Hydration.
Hydration of what? Right. So we need to figure out where the double bond needs to go in order to obey Markovnikov's rule and make the OH go right here. Well, right here. So there are two choices that would work. There are two reactions that would give us the desired product. What's one of them? Where's one place you could put the double bond?
The second one, carbon number 2.
Carbon number 2? Yep. So 1, 2, 3, 4, 5, 6, 7. And then you still need to have those methyl groups, right? Those have to already be built in. Right? Because Markovnikov's rule is going to say, okay, the hydrogen will go.
Oh, are you asking me?
Mm-hmm.
On that one, it doesn't matter, does it?
Well, on this one, yeah, you're going to get a mixture, right? You're going to get some that have it here, the OH here, and some that have the OH here. So this would give you two products. It'd give you this product, and it also give you the version where the OH is up here. Okay, so this would give you two products, which you then have to separate. Do you need a catalyst? H+. And what's the name of this?
2, 3 dimethyl,
2-heptene, right? Okay, there's another way that you could do this where you'd only get one product. If you had the double bond right here, right? 1, 2, 3, 4, 5, 6, 7. And you have the double bond here, plus H2O. Now, Markovnikov's rule is going to say hydrogen's going here, OH is going here. This would only give you one product. So if I asked you which one's better, right, this one would be a better choice. Because if you do it this way, you're going to get two products. If you do it this way, you're only going to get one. So this would be the better choice. But I would have accepted that if you wrote it. And then what's the name of this molecule?
2, 3 dimethyl, 3 heptene.
Right. It's better to have the double bond here just because you're only going to get one product versus two.
I didn't know how to do that.
Okay. let's talk about it. So in the next one, potassium permanganate is a strong oxidizer. Write the reaction that occurs when KMnO4 is added to the same thing that we just made. 1, 2, 3, 4, 5, 6, 7. Now KMnO4 will oxidize the living daylights out of a lot of stuff. But let me ask you this. When you oxidize a secondary alcohol, you get a ketone. What kind of alcohol is this? It's tertiary. Can you oxidize a tertiary alcohol? Right, it's no reaction. No reaction. You cannot oxidize a tertiary alcohol. So, no reaction. You can throw whatever oxidizer you want, right? If you were to make this into a double bond, can't do it. There's no hydrogen here to oxidize.
So whenever it's like added to it, it's not plus KMnO4.
You could write it that way.
It's the same thing.
Because remember, when we write an oxidation, you can either write the O in brackets on top of the arrow, or you can just write what the oxidizer is.
Like, I mean, you don't add it like you add H2.
You can just write it over the arrow, that's fine. But do you understand why this is no reaction?
Yeah.
Because it's tertiary alcohol, can't oxidize tertiary alcohol. Doesn't matter which oxidizer you pick, it's not going to work. Nothing there to oxidize.
So then what happens? Like, it doesn't change at all?
Nothing, no reaction, yeah. They just sit there. Okay, 2-methyl cyclohexene is what we want. 2-methyl cyclohexene. All right, so there are 2 ways you could do this. What's one way you can make a double bond? Using an alcohol. What?
Oh, or hydration.
Dehydration, right? Dehydration. If this is what we want, right? Let's think backwards. Where do we have to have the alcohol, the OH group? Think about Satsev's rule. So that's what we want. So let's just write a reaction going this way. All right, we know we need a methyl group in there somewhere, right? If we had this and we dehydrate that, Satsev's rule says you're going to get the double bond here or you're going to get the double bond here. That's the same molecule, right? That would give you your desired product plus H2O. There's another way we could do that. If we had that OH here, would that work?
Yeah.
Because Satsev's rule is not going to apply to this one. Here, Satsev's rule would apply. The more substituted alkene is the favored. That's the major product, right? So you will get your product, and it'll be your major product. But you will get a small amount of the other product. There will be a tiny amount on the side. Right here, you're only going to get one product. Here, you're going to get a major product as what you want. Do you see how this works?
Yeah, I don't understand how you knew there was an alcohol group on there when it was hexene instead of hexene.
So if you think back to last lecture when we talked about alcohol reactions, the last one we talked about was dehydration of an alcohol, getting your alkene back.
Oh, gotcha. Okay.
Now there's another one that would work too. Did you think of it?
I didn't put an alcohol on it, so I don't think mine was right.
If you want this, that's the same thing as this. Does that look familiar?
Is that
Diels-Alder would work too. All right, because if you go A, B, C, D, E, F, what would produce that? A diene with a methyl group right there, that would give you your product. A, B, C, D, E, F. So I would have accepted either one. That's only going to give you one product too. All right, last one. We're using potassium permanganate again. That's a nice strong oxidizer. Cyclopentanol, 2-chloro. When we oxidize a secondary alcohol, can we oxidize a secondary alcohol? Yep. What are we going to get? A ketone, right? All right, so the type here is oxidation. And this would be 2-chloro-cyclopentanone. We haven't named ketones yet, but preview of things to come. Right now, all you'd be responsible for is knowing that it's oxidation. We'll do naming ketones really soon.
Whenever it's in a ring, can you only get ketones? You can't get an aldehyde.
Unless it were like this. If it were coming off, then you would get, that one would get oxidized. The primary can get oxidized to an aldehyde. But yeah, in a ring, a secondary can only become a ketone. Yep. Feeling all right about this stuff? All right. That's where we're going to stop for today. So